Okay, so for this lesson today, we are going to start getting into the different types and classifications of your different refrigerants that are commonly found in your air conditioning and even in some of your refrigeration equipment. So today, refrigerants have really expanded in their different chemical makeups and different categories. I know when I first got into the field, we didn't have as many as these as we see here. We had the CFCs, we had the HCFCs, we had your Azeotropic, your Zeotropics. We definitely had some of your HFCs, but these HFOs and the HCs refrigerants that are now listed are new types of refrigerant that's coming out and will eventually be probably seen a lot more probably in the next couple of years, depending on how the operation and things go with them. So we have really a couple different types that are out there. We have our chlorofluorocarbons, as like I said, is a CFC refrigerant for short. Hydrochlorofluorocarbons, yeah, say that 10 times fast. That's HCFCs. Then you have your hydrofluorocarbons, HFCs. Then you have different refrigerant blends, which are refrigerants that are made up of different refrigerants together at different percentages, and those are broken down into your azeotropic and zeotropic type refrigerants. And then you have your hydrofluoroolefins, which is an HFO, and then your hydrocarbons, which is an HC. So in regards to your HFC refrigerant, these were kind of like the first refrigerants that were really developed when we started using refrigerant in HVAC. HFCs have been used as blowing agents for the manufacturer of insulation and packaging. So they've been used for quite a different things over the years. But really what the HFCs are made up of and composed of is your chlorine, fluorine, and carbon. Now what's good about knowing the different types of composition for each one of your refrigerants is that it kind of piggybacks on to your EPA certification. Because in EPA they ask you some chemical makeups of some of your refrigerants and what it's made up of and what damages the ozone layer and all that other stuff. So knowing the type of refrigerant you're dealing with is kind of good to know when it comes to actually working with it and where you're actually going to find it. So commonly you have two popular, I should say actually, CFC refrigerants that are out there. You have your R11 and your R12. Those are the really old refrigerants. You'll probably find them in really old refrigerators and in cases even some really old air conditioners. But those are your CFC refrigerants. These types of refrigerants are no longer manufactured. And if you do have to purchase it, you do have to pay. It's a pretty hefty price to purchase it and have it. But most of the time now you probably really won't run into it too often. But you know, you never know. It's something that you have to kind of still keep in the back of your mind, because unfortunately the older equipment that was out there, that stuff was built to last. Versus the newer equipment where if it breaks, you got to either replace it or you got to constantly repair it. Okay, when CFCs are vented though into the atmosphere, it's the chlorine atom that it's made up of that attaches to oxygen atoms in the ozone. Okay, and that combination is what actually breaks down the ozone molecules. Okay, each chlorine atom can break apart as many as 100,000 ozone molecules before it neutralized through other chemical reactions. So with regards to EPA, it is the chlorine atom that is the reason for the depletion of the ozone layer and for greenhouse gases and, you know, ultraviolet radiation and all that stuff, is because when we vented before we actually had to follow recovery techniques and reclaiming and all that stuff, we used to just be able to open up the valves and just let the refrigerant go. Can't do that anymore. We have to make sure that we recover all of the refrigerant into a external storage cylinder and then dispose of it properly. Okay, so the result of that chlorine atom breaking down the ozone layer is obviously the reduction of the ozone, and it also increases the ultraviolet radiation reaching the earth. So what happens is that CFC refrigerant has a really high ozone depletion potential, ODP, and is probably one of the major causes for ozone depletion. Okay, the ODP is a numeric value assigned to the refrigerant that provides a clear perspective in the amount of ozone depletion caused by that refrigerant. So it's good to know some of these things when it comes to working with the refrigerant. But bottom line is, regardless of the type of refrigerant that you're dealing with, you still have to recover it, reclaim it, recycle it properly. EPA does not want you venting refrigerant at all. We have to take it out of our system and store it in a external cylinder and do it safely and with obviously the correct techniques. So ODP scale has a minimum value of 0 and compares the destructive potential of different chemicals to the destructive potential of R11. Okay, and R11, which is 1 on the ODP scale. Okay, so by the international agreement, they must not have been manufactured in developed countries since the end of 1995. Okay, that international agreement was called the Montreal Protocol. It was that international agreement that said, hey, we are no longer going to manufacture these types of refrigerants. Okay, but however, some CFCs may still be found in some air conditioning and refrigeration equipment produced before 1995. So the refrigerant is still out there. It's probably not as popular anymore, but some of the old equipment that is like out there, like it says here, like before 1995, you're probably going to run into it. If you can never read the nameplate of the type of refrigerant that is in a piece of equipment, you can always go by the model and serial number. Everybody has a smartphone, you know, iPad, some sort of electronic device where you can punch in these numbers and do a little bit of research, do a little Googling to find the type of refrigerant that you're actually dealing with. Okay, HCFC refrigerants, hydrochlorofluorocarbons, or better known as HCFCs, is a refrigerant that is composed of hydrogen, chlorine, fluorine, and carbon. HCFC molecules include a halogen, halogens combined with either methane or ethane. That's actually in there. Okay, so some examples of your HCFC refrigerant is obviously the common R22, which is found in a lot of your air conditioning, and R123. However, studies have indicated that HCFC refrigerant and refrigerant blends have less impact on the ozone layer than fully halogenated CFCs. Okay, CFC refrigerants is considered to be fully halogenated because all of the hydrogen atoms in the original methane or ethane molecule have been replaced by halogens such as chlorine and fluorine. So what they have actually done in some of these cases is they actually remove the chlorine atom from it completely And when they remove the chlorine atom from it completely, they say that it is actually ozone, quote unquote, ozone friendly. So HCFCs are considered to be partially halogenated because not all the hydrogen atoms have been replaced by chlorine and fluorine. So here we are. If we look at this chart here, we have a CFC, which is an R11. So we have our methane-based molecule, which is only one carbon atom. Then we have our halogens replacing hydrogen, which is our fluorine and our chlorine. So as we start to develop these refrigerants in a little better chemical composition, they were said to be better and ozone friendly and all that other stuff. So as we start to remove the chlorine atom, as we get into this a little bit more, you'll see that the ODP and stuff like that actually will change. So with the HFCs, you'll see that they are now starting to take away that chlorine atom. So HCFC refrigerant tends to break down in the lower atmosphere and cause less ozone depletion than your CFCs. However, HCFCs linger in the atmosphere for a longer time and have a higher GWP, or global warming potential. Okay, your global warming potential is a rating based on the warming effect of a substance warming effect compared to the warming effect of carbon dioxide. So EPA requires the complete phase out of all HCFC refrigerants by the year of 2030. So you will start to see these refrigerants start to really go away, and it's going to be just like the CFC refrigerant, where you're probably going to be paying an astronomical amount of money if that refrigerant needed to be put back in or what have you. But chances are by 2030, the refrigerants that have HCFC refrigerants will probably just be simply replaced and taken out with newer units. So that's going to be their way around a lot of this stuff. So here is a chart that deals with different environmental properties of different refrigerants. So like R11 has an ODP of 1, but yet it has a GWP, or a global warming potential, of 4,750. R22 has an ODP of 0.05, but has a GWP of 1,810. Okay, so these charts here just gives us a breakdown, and if you notice with our R134A, which is an HFC, they take away the carbon out of it. It has an ozone depletion potential of 0, but they still have a global warming potential still in the thousands. So regardless of whether we have the carbon atom in there or not, the refrigerant still has some sort of effect on the Earth's atmosphere. So, which is why your EPA tells you to recover your refrigerant and don't vent it. Okay, your HFC refrigerants, which is your hydrofluorocarbon, is made up of hydrogen, fluorine, and carbon. Okay, they are different from your CFCs and your HFCs because they do not have the chlorine atom. So HFCs, again, are considered to have a 0 ODP and are partially halogenated, but they have a lower ODP than HCFCs because they do not contain the chlorine atom. So a lot of your HFC refrigerants that are out there is your 134A, your 152A, and your 404A. Okay, even though HFCs have a ODP of 0, some HFCs have a high GWP and are, again, beginning to be replaced by a variety of lower GWP alternatives, such as carbon dioxide, hydrogen carbons, and your HFOs. Your HFOs are similar to your HFCs, again, because they contain hydrogen, fluorine, and carbon. They are slightly different due to their chemical makeup and chemical structure, but they still have different properties in different areas where we think that they may not necessarily be as quote-unquote ozone friendly and environmental friendly. So your refrigerant blends, these types of refrigerants are made up of 2 or more established refrigerants. Okay, and you have 3 different groups that they are actually breaking down to based off of their thermodynamic properties. Okay, you have your azeotropic, your zeotropic, and near azeotropic type blended refrigerants. Okay, refrigerant blends fall into the same chemical classifications as the individual refrigerant of which they are composed. So if a refrigerant blend has a CFC, it's classified as a CFC. If it has an HFC or an HCFC but no CFC, it's then a HCFC. Okay, so R500 is actually composed of R12, R152A. So 152A is an HFC, but R12 is a CFC, so therefore R500 is considered to be a CFC. Okay, some of your most common blends that are out there, you got your R12, R22, and 134A. Your azeotropes are refrigerant blends that respond to change in pressure and temperature, like a single refrigerant, having fixed boiling and condensing points when it's running through the refrigeration cycle. Your azeotrope refrigerants maintain consistent properties during all operational conditions. At atmospheric pressure, the refrigerant will not separate as the blend evaporates and condenses. So azeotropes are identified by their ASHRAE identification number series of 500. The 500 consists of R12 and R152A. R502 consists of R12 and R115. So your zeotropic blends, these are refrigerant blends in which individual refrigerants that make up the blend responds differently to conditions based on its individual characteristics. Zeotropes operate under a range of boiling and condensing points that correspond to the range of its individual refrigerants and the percentage of the blend that each refrigerant actually makes up. So R12 and R22 boil and condense at the exact same pressure and temperature point. So geotropes boil and condense at different temperatures. So the difference in boiling and condensing temperatures is due to fractionation. So when we are dealing with zeotropes type refrigerant, we need to make sure that we are putting that refrigerant in the system as a liquid. We cannot put it in as a vapor. If we put the refrigerant in as a vapor, we risk that fractionation, which means we are not putting in the equal amount of each individual refrigerant that it actually makes up. So charging by a liquid kind of ensures that we are getting a good mixture of all of the refrigerants that it actually makes up. Okay? So during the refrigeration cycle, if we didn't do this correctly, a single geotrope refrigerant can separate into its individual component refrigerant. And when that happens, it's going to mess up your temperatures and your pressures, and the system is just simply not going to work correctly. Okay? The separating of your zeotropic refrigerants into their own individual refrigerants is called fractionation. When fractionation can be thought of as the refrigerant splitting up or fracturing into its base components. Okay, this occurs because the different refrigerants in zeotropic blends have different boiling points. The refrigerant with the lowest boiling point is going to boil off first. With that way, we could figure out different boiling points of the different refrigerants is by using a temperature pressure chart. That temperature pressure chart gives us a baseline temperature and a baseline pressure at which that refrigerant is doing a specific task. The temperature at which a liquid zeotrope refrigerant first begins to boil is called its bubble point. Okay, so for example, R401A is a zeotropic refrigerant because it's composed of R22, R152A, and R124. So at atmospheric pressure, R22 has a boiling point of negative 41 degrees Fahrenheit. R152A has a boiling point of negative 13. R124 has a boiling point of 10.5 degrees Fahrenheit. Okay, as the refrigerant blends, enters the evaporator, it's going to be the R22 that's going to vaporize first. Then it's going to follow the R152A. So the temperature at which the vapor zeotrope first begins to condense is called its dew point. The impact of fractionation in a zeotropic refrigerant can have different temperatures at any given pressure depending on whether it is a liquid or a vapor. Okay, so it's really important to understand what can happen to the system and the refrigerant operation in a specific type of unit that actually uses a zeotropic refrigerant. It is important to understand that if fractionation occurs, you're not going to achieve the correct temperatures or the correct pressures in your evaporator or your condenser or even in your metering device. Okay, the temperatures between the temperature difference is called your temperature glide. Okay, the temperature glide is the temperature difference between the vapor and liquid state during evaporation and condensation at a constant pressure. Okay, a common range of temperature glides is anywhere between 0.3 degrees to up to about 10 degrees, depending on the refrigerant that you are dealing with. Okay, so never attempt to make your own mixture of refrigerants. Okay, azeotropic and zeotropics are patented refrigerants, and the manufacturing process is very complicated. So don't try to be one of those mad scientists out there and try to mix R22 with R410A and see what happens. It's probably not going to end very well. So if a unit uses R22, you put R22 in it. If a unit uses 404A, you put 404A in it. If it uses 410A, you put 410A in it. Don't be some sort of genius and try to fix stuff and make your own stuff. Okay, near zeotropes react similarly to zeotropes but respond over a smaller range of boiling and condensing points. Near azeotropes are technically zeotropes, but allowing them their own category helps to differentiate them more precisely. Okay, your HFOs, or hydrofluoroolefins, is a new category of refrigerant, and these are also composed of hydrogen, fluorine, and carbon, but have at least one double bond between the carbon atom. That's what makes them different. HFOs are technically a group of HFCs, but are made from olefins rather than alkanes. Okay, HFOs have a 0 ODP and lower GWP values. You will see HFO refrigerants being used in automotive air conditioning, and when they are used in automotive air conditionings, they are mixable with a POE lubricant and are not soluble with in mineral oils or alkali benzene type lubricants. Common types of HFOs that are out there now is your 1234YF and your 1234ZE. Okay, these refrigerants have a low toxicity but are slightly flammable with an ASHRAE safety classification of A2L. The L actually stands for lower flammability. Okay, your HFO 1234YF is being used as a low GWP replacement for 134A in automotive air conditioning. The 1234ZE is designated to replace R410A in residential and light commercial air conditioning heat pump applications. Okay, it can also be used in air-cooled and water-cooled chillers in supermarkets and commercial buildings. It is energy efficient and requires minimum retrofit work for existing type of equipment. Probably, I think the most that you may have to do is maybe replace the metering device and maybe the oil. I don't know a whole heck of a lot about these types of refrigerants because I obviously have not really worked on them too much, but these are coming out and eventually will probably be taking over the market probably within the next couple of years. Your HC refrigerants is a hydrocarbon, or organic substances that contain carbon and hydrogen. These substances are the components in petroleum and natural gas. Your HC refrigerants have an ASHRAE safety classification of an A3, and only some HC refrigerants have been approved by SNAP. SNAP stands for Significant New Alternative Policy. SNAP is a EPA program that evaluates and regulates substitutes for high ODP refrigerants, and your HCs use in new equipment is under very limited conditions, such as small refrigerant charges, and we're talking probably only a couple of ounces as of right now. Most of the equipment that you may see these in is your standalone retail refrigerators, your freezers, some domestic refrigerators, and freezers. Some HCs refrigerants that have been approved by SNAP is your R600, which is an isobutane, R290, which is a propane, and your R441A, which is an HC blend of, I do believe, both your R600 and your 290.